Okay, now for question Phil, which is worth 20 points. The question is, lithium has a +3 nuclear charge. It's got Z equals 3, and we're going to consider doubly ionized lithium, lithium double plus. In other words, we have a single electron near the lithium nucleus, making this a hydrogen-like system. First key realization for the question. So first ask, what is the Schrödinger equation for the electron? So we got to think back just a little bit and remember the Schrödinger equation here. So first of all, the potential is going to be -2 Rydbergs times the Z value, which is 3 divided by the radius of the distance from the nucleus. So the absolute value of the radius, which actually is always positive anyway. So the potential is -2 Rydbergs is attractive times 3 R, or -6 over R. Now the Schrödinger equation itself is H psi equals E psi, and H is just equal to minus H bar squared over twice the mass times del squared times the curvature. Now -6 Rydbergs times 1 over R times psi equals E psi. That's all. So H psi equals E psi. You have to figure out what the potential is to split the Hamiltonian into its kinetic energy term, which is always going to be minus H bar squared over twice the mass times the second derivative operating on the wave function, and then you put in the potential, and that's equal to the total energy. Now, second question. 4 points. What's the energy level expression including all quantum numbers and their allowed ranges? Well, the energy is going to be minus Z squared times Rydberg constant for hydrogen. That's 1 over N squared. That should be a squared, sorry, is equal to -9 Rydberg constants times 1 over N squared for N equals 1, 2, 3, etc. out to infinity. Okay, the other quantum numbers are going to be L, which can go from 0 to N minus 1, and M sub L, M sub Z, which can go from -L through 0 to L, and finally M sub S, which can be plus or minus 1/2. So those are all the allowed quantum numbers and their allowed ranges. Now, what is the energy of the ground state in wave numbers? Well, the ground state's N equals 1, so the energy is going to be -9 Rydbergs. That's -9 times 109,737 wave numbers. And doing a little math here, carrying, we get 987,633 wave numbers. I actually did that. I'm not going to take off many points if you don't do the math, but it's pretty darn easy to multiply 9 by a number and carry a couple things, and you get a final answer. Part 4. What's the characteristic distance of the electron from the nucleus in Bohr radii? Well, that goes like E, and then it's going to be -ZR over A naught, and so that's going to be E to the -3R over A naught. So the characteristic distance is going to be 1/3 of a Bohr radius. Every time you add a charge, you pull in that characteristic distance by an amount equal to that charge. So it's going to be on the characteristic distance of the electron away from a lithium double plus is 1/3 of a Bohr radius. Finally, let's write an expression for the wave numbers of light absorbed by lithium double plus initially in the 3p1 state. So 3p1, that's N equals 3. That's the important part. Also, we're absorbing light, so we have to go from N equals 3 to a higher value of N because the energy has to go up. So the wave numbers are going to be -9 Rydbergs times 1 over the final quantum number minus 1/9, where the final quantum number is 4, 5, 6, 7, 8, 9 through infinity. So that's going to give us the overall value there. And notice when N is equal to infinity there, the wave numbers are going to be equal to just exactly 1 Rydberg, so that works out looking a little bit like Lyman alpha of hydrogen.